Hello everyone, in continuation of our metal calibration course in week 9, we are going to cover 4 topics majorly. Phase in coming under X-ray diffraction, is phase identification, next determination of crystal structure, then we will cover quantitative phase analysis, then stress measurement. So starting with phase identification by X-ray diffraction. For a given substance, always it produces a characteristic diffraction pattern whether that substance is present in the pure form or in some form of mixture. So on this fact, the for the diffraction method, qualitative analysis for a particular substance is accomplished by identification of pattern of the substance. Along with the qualitative analysis, there is also possible to do quantitative analysis because the intensity of the diffraction line due to one phase of a mixture depends on the proportion of that phase in the specimen. So every substance have characteristic diffraction pattern and with the help of that we can do qualitative as well as quantitative analysis. This is accomplished by identification of pattern of that substance. And quantitative analysis, because of the intensities of diffraction lies possible because intensities of diffraction lines due to one phase of a mixture depend on proportion of phase in the specimen. So what is the advantage of diffraction analysis? It discloses the presence of a substance as that substance actually exists in the sample and not in terms of the chemical elements. For example, if sample contain two compounds A and B with constituent, let's say A has X in the mixture, A has X proportion and B has Y proportion, then the diffraction method will disclose the presence of AX and BY as such, whereas the chemical analysis would show only the presence of elements A and B and not their proportion. So that we can say that's why the diffraction analysis is somewhat better than chemical analysis. Advantage of diffraction analysis over chemical analysis is diffraction analysis discloses the presence of a substance as that substance actually exists in the sample. And not only in terms of constituent chemical elements. Like if A has X proportion, B has Y proportion, then whole information we will get from diffraction analysis. But in chemical analysis, we will just know that the A compound is present and the B compound is present. In chemical analysis, it will only tell us A and B components are there, but how much, in what proportion, that we will not able to get in chemical analysis. So considering the basic principle for seeing these phases, the powder pattern of a substance is characteristic of that substance and forms sort of fingerprint by which the substance uh, is identified. So a collection of diffraction pattern from many substances allow identification of unknown by recording its diffraction pattern and then locating it in a file of known patterns, one which matches the pattern of the unknown exactly. So the collection of known pattern has to be large if we are going to look at any random sample. So what is the need of such a system of classifying the known patterns so that one can match the unknown and easily identify a substance? And such uh, kind of system is devised by Hannawelt. So there what it's done is any one powder pattern is characterized by a set of line position 2 theta and a set of relative intensity I by I1 and a set of relative intensity scaled to uh, peak in the pattern with maximum intensity. But the angular position of line depends on the wavelength used and for which we need the value of d, that is the lattice spacing between the lattice planes. So Hannawelt, what he did, he described each pattern by listing the d and l value of a diffraction line and arranged the known pattern in decreasing value of d for the strongest line. So this arrangement is helps us to search lot of unknown samples. So uh, what Hanaman did, he described each pattern by listing D and N values of its diffraction lines and arranged the known patterns in decreasing values of D for strongest line in the pattern. And this arrangement made possible to search quickly, look at the crystal structure of substance, the unknown crystal structure of substance. So in identification, the basic principle behind it collection of diffraction patterns for many substances allows identification of a known by recording its diffraction pattern and locating that in the file of known patterns where it matches the unknown exactly. The procedure involved in such process is first, after getting the experimental values, first experimental values of D and the ratio of intensities, where here the relative intensity where here I1 is peak pattern with maximum intensity. These are first collected and stored, and to identify the unknown, first we locate the proper D1 group in search manual. Then we read down the second column of D values to find the closest match to D2. Then after the closest match, found for D1, D2 and D3, the relative intensities are compared with tabulated values. Then when good agreement is found, for lines listed in the search manual, then we look at the proper PDF card. Where here PDF means powder diffraction file and compare the D and relative intensity ratio values of all the observed lines with those that is tabulated. So when full agreement is obtained, then identification is complete. So let's see how we can identify such differences in different phases. So for the identification of single phase samples, so when the unknown is single phase, the search procedure is straightforward. Like for example here, this pattern of unknowns is obtained using a copper K alpha radiation. It's obtained through copper K alpha radiation. Here the experimental values of D's and I by I1s are written. So if we will see here the experimental values of, let's say, D1, D2 and D3 respectively, 2.8 to 1.99, yeah, 2.8 to 1.99 and 1.63. And by examining the numerical search manual, strongest line is found to fall is within 2.84 and 2.80. For the group of D1 values, and for D2 similarly we can find for D2 and D3 here in table 2. For NaCl we can see 5 values for D3 equals to 1.63. So here we can note that the intensity listed for the 3 strongest line of this substance, they agree fairly well with the observed intensity. So do so as the data for other 5 lines. So if we see the PDF card and we compare the complete pattern, it is in good agreement, but there are some discrepancies, and these discrepancies can be resolved before identification it as a NaCl. A weak line with D equals to 2.18 not listed in the file card is observed, and calculations show that this line is a 220 reflection of copper K beta radiation, and that is not removed by the filter. And another stronger radiation, stronger 200 reflection, that will also produce K beta line, but this K beta line fall on the 111 K alpha line, and that is why it is not separated. And the 331 line corresponding to D equals to 1.294 is not observed because its intensity is expected to be very low, and two high angle lines corresponding to D equals to 0.79 and 0.78 are observed but are not listed in the PDF card, because most often the file card data, they do not extend it to highest accessible 2 theta values, but they can be indexed as 711, 511 and 640 lines, which are expected lines after 444 in the FCC sequence. So similarly, because the discrepancies are understood, and we can identify it as NaCl completely. A few unexplained weak lines are often assumed to be due to unknown impurity. The identification of main constituent is then somewhat tentative, and they depend on how experienced we are. So because small d spacing correspond to back reflection line, their measurement with greater precision than larger d spacings. Spacing smaller than 1 angstrom uh, should therefore be computed to the nearest 0.001 angstrom rather than 0.01 angstrom. That much precision we should keep while measurement. Then identification of phases in mixtures. It is somewhat more complicated than identification of phases in single phase material. Here we can see this is pattern obtained from copper K alpha radiation and a diffractometer, for which D1 is given as 2.09 angstrom, D2 is given as 2.47 angstrom, and D3 is given as 1.8 angstrom. The examination of numerical index in the D1 group varies from 2.09 to 2.05 angstrom, and that reveals several substances having D2 values near to 2.47 angstrom, but in no case the three strongest lines taken together agree with those of the unknown. So this impasse suggests that the unknown is actually a mixture of phases, and that is incorrect to assume that the three strongest lines in the pattern of the unknown are all due to same substance. Let's say we see the strongest line D equals to 2. Consider strongest line D equals to 2.09 and the second strongest line 2.47 angstrom. They are formed by two different phases, and that the third strongest line corresponding to (1.80 angstrom) is due to the first phase. So if we assume that D1 equals to 2.09 and D2 equals to 1.8 for one phase, in a search of the same group of D1 values, but now in the vicinity of D2 equals, which is 1.80, they are in agreement between the three strongest line of pattern of copper. So if we look at the PDF card, all lines of the copper pattern agree with table 3, the pattern of the unknown. One phase of the mixture is thus shown to be copper, providing that remaining of the lines can be assigned to some other substance. These remaining lines we can see here. By multiplying all the observed intensity by normalizing factor, the intensity of strongest line is increased, and searching the index and PDF for the same tells us that the remaining line agrees with the pattern of cuprous oxide. So the unknown is a mixture of copper and cuprous oxide. So the analysis of mixture becomes more difficult when a line from one phase is superimposed on a line from another, and when this composite line is one of the three strongest lines in the pattern of the unknown. The usual procedure then leads only to a very tentative identification of one phase, in the sense that the agreement is obtained for some d values but not for all the corresponding intensities. So this in itself is evidence of line superposition. So such patterns can be untangled by separating lines which agree in d value with those of unknown phases. The observed intensity of any superimposed lines being divided into two parts, one assigned to the unknown phase and the balance together with the remaining unidentified lines iterated in as we solved it for single phase material. So this is one of the some of the ways we can identify the phases in our XRT pattern. Next, coming to determination of the crystal structure. The basic principle involved in structure determination is, as we know, the crystal structure of a substance determines the diffraction pattern of the substance, or in other words, we can say shape and size of the unit cell that determines the angular position of diffraction lines and arrangement of atom within the unit cell. So if we say the crystal structure, we are considering unit cells and that correspond to line positions. So here, the shape and size of unit cell determines the angular position, or you must say, of the diffraction line, and arrangement of atom within the unit cell determines the relative intensity of the lines. So the determination of unknown structure can be done in following way. First, the shape and size of the unit cell are deduced from angular position of diffraction line. Shape and size of the unit cell are deduced from angular positions of the diffraction lines. So here one assumption is first made as to which of the 7 crystal systems the unknown structure belongs to, and then on the basis of this assumption the correct Miller indices are assigned to each reflection. First, one assumption for unknown structure is made, which crystal system it belongs to. From 7 crystal systems. And then accordingly Miller indices are assigned to it. This step is called indexing the pattern. Then the number of atoms per unit cell is computed from shape and size of the unit cell and chemical composition as well as its density. Then finally the position of the atoms within the unit cell are deduced. Position of atoms within the unit cell are deduced from the relative intensities of the diffraction line. Only when these three steps are accomplished, then the structure determination is complete. So the indexing patterns of cubic crystal so for cubic crystal the diffraction lines we will get from Bragg's law would satisfy this equation. As this s equals to s square plus k square, so s square should be integral, and this lambda square by 4a square is a constant for any one pattern. The problem of indexing the pattern of a cubic system is one, finding a set of integer for this s, which will give us a constant quotient when divided by sine squared theta values. So the numbers which can be discarded from this squared sum is obvious because numbers like 7, 15, 23, this cannot be obtained using this pattern. So from this we can say for simple cubic we get values like 1, 2, 3, 4, 5, 6. For body centered we get values like 2, 4, 6, 8, 10. For face centered we get values like 3, 4, 8, 11, 12. And for diamond like zinc blend structure 3, 8, 11, 16. So here each set can be tried again and again, and if a set of integer is not found, then substance involved doesn't belong to that cubic system, and we have to look for other system other than cubic system, non-cubic systems like tetragon and hexagon. So for indexing patterns of non-cubic crystals, the first example we consider tetragonal system. For this, sin square theta must obey this relation a h square plus k square c l square, where here a is lambda square by 4a square and c is lambda square by 4c square, and these are two constants for any one pattern. So now the problem is to find these constants. So once these constants are found, they will give us the values of A and C, and we can complete the indexing process. So how this A is can be found? For A, we take HK0 line, and when L is 0, sin square theta is A h square plus k square, and the permissible values for h square k square 1, 2, 4, 5, 8. So this HK0 line must have sin square theta values in ratio of this integer, and A will be having value 1, 1 by 2, 1 by 4, 1 by 5, 1 by 8, and so on, times this sin square theta. And similarly C can be obtained. If we replace the CL square 2 sin square theta minus A h square plus k square, and for here we can say it should be of a ratio for 1, 4, 9, 16 and so on. This is for tetragonal system. For hexagonal system, this should satisfy sin square theta equals to a h square plus hk plus k square plus cl square, where here a is lambda square by 3a square and c is lambda square by 4c square. Now we will be having the problem of solving for this a and c, which will be two constants, and after finding we can index our crystal system very easily. Similarly, for orthorhombic system, this should satisfy the equation tan square theta equals to a h square plus b k square plus c l square. Now here we have to find out this a, b and the c. And for monoclinic and triclinic, they involve four. Monoclinic involves 4 constants and triclinic involves 6 independent constants. And accordingly we can find those constants and then index our system accordingly. Now moving on to the next topic, quantitative phase analysis. So this basic principle of multi-phase quantitative analysis involves, as this quantitative analysis is based on the fact that the intensity of diffraction pattern of a particular phase in a mixture of phases depend on the concentration of that phase in the mixture. So the relation between intensity and concentration is not generally linear. Why? Because the diffracted intensity depends on the absorption coefficient of mixture, and this varies with the concentration. It is based on the fact that intensity of diffraction pattern of a particular phase in a mixture of phases depends on the concentration of that phase in the mixture. So to find the relation between this diffracted intensity and concentration, so we consider this equation for intensity diffracted by powder specimen, and the form of this equation depends on what kind of apparatus you are using, like what kind of diffractometer you are using. So for single phase, for single phase powder specimen in diffractometer, the intensity is given by I0 A lambda cube divided by 32 pi r times mu naught by 4 pi squared e to the power 4 divided by m square times 1 by b squared times f of HKL squared times p of 1 plus cos square 2 theta by sin square theta cos theta times e to the power minus 2n by 2 mu. Where here IHKL is the integrated intensity per unit length. Its unit is joules per second per meter, and here I0 is the intensity of incident beam. A is the cross-sectional area of intensity beam, and lambda is the wavelength of the incident beam. R is the radius of diffractometer circle, and mu naught is basically 4 pi into 10 to minus 7. E here charge of electron, and here m is the mass of electron. B is the volume of unit cell, and here FHKL is the structure factor for reflection from HKL plane, and here P is the multiplicity factor, and here theta is the Bragg angle, and here e to the power minus 2m basically temperature factor, and here mu is the linear absorption coefficient, here this equation applies only to a pure substance. So, but if let's say we analyze a mixture of two phases, then this equation can be written in terms of one particular line of alpha phase, and here IHKL will become the intensity of selected line of the alpha phase, and this I alpha HKL multiplied by a factor C alpha, the volume fraction of alpha in the mixture, to allow for the factor diffracting volume alpha in the mixture, which is less than it would be if the specimen were pure, and mu m is replaced by mu. So here our intensity is modified by K1 C alpha by mu m, where here C alpha is the volume fraction of alpha in mixture. Here basically we are considering two phase mixture. Here mu m is the linear absorption coefficient of mixture, and all factors are constant and independent of alpha. So here K1 is basically unknown, and as it is related to I0 and I0 is unknown, so K1 is unknown. But this I alpha becomes unimportant if the ratio of I alpha to the intensity of some standard reference is formed, and then we can find the concentration of alpha from that. So there are three ways we can compare this I alpha, and we will get different results. So three methods of analysis for that reference line. First is external standard method. This is a line from pure alpha. Next we have direct comparison method. Here a line from another phase in the mixture. Third, internal standard method. A line from a foreign material mixed with specimen. Coming to external standard method, here this equation I alpha equals to K1 C alpha by mu n. This mu n expressed in terms of concentration, where here W denotes the weight fraction and rho denotes the density. As I have told, we have a mixture of two samples, alpha and beta, so we are distributing it accordingly. weight fraction and so density. Well, let's consider a unit volume of the mixture. So its weight is rho m, and the weight of alpha contained alpha is W alpha rho m. Therefore, the volume of alpha is W alpha rho m by rho alpha. So weight of contained alpha is given by W alpha rho m, and volume of alpha is given as W alpha rho m by rho alpha. So mu m becomes C alpha mu alpha plus C beta mu beta alpha plus 1 minus C alpha mu beta becomes C alpha mu alpha minus mu beta plus mu beta. So our intensity modified to by C alpha mu alpha minus mu beta plus mu beta. So this equation relates the intensity of a diffraction line from one phase to the volume fraction of that phase and the linear absorption coefficient of both the phases. So if we will, on a weight basis, we will consider a unit mass of mixture, then the volume of contained alpha is W alpha rho alpha and the volume of beta is W beta rho beta. So C alpha we can write it as W alpha by rho alpha by rho alpha plus W beta by rho beta by using this equation we can write intensity I alpha as K1 W alpha by rho alpha W alpha times mu by rho of alpha minus mu by rho of beta plus mu by rho of beta. So for a pure alpha phase, we will get alpha pure as K1 by mu alpha, pure alpha phase, and if we will divide this with alpha, then we can get rid of the unknown K1, get the equation W alpha mu by rho of alpha by alpha W alpha mu by rho of alpha minus mu by rho of beta plus mu by rho of beta. So this equation permits the quantitative analysis of two-phase mixture, provided that the mass absorption coefficient of each phases are known. These are known. These are known quantities. Then only we will be able to find. So if they are not known, a calibration curve can be prepared by using mixture of known composition, and in each case a specimen of pure alpha must be available as a reference material, and the measurement of I alpha and I alpha beta I alpha pure must be made under similar kind of conditions. For direct comparison method, this method doesn't require a sample of pure phase because the required reference line comes from another phase in the mixture. So it is of great interest because it can be applied to polycrystalline aggregates too. So to start with, in the basic intensity equation, K2 is given by I0 A lambda cube by 32 pi r times mu 0 4 pi squared e to the 4 by m square, and r is denoted as 1 by p square. Basically we are just splitting our equation of intensity. Then we can write our intensity as K2R by 2 mu, where K2 is a constant independent of kind and amount of diffracting substance, and R depends on theta, HK, and kind of substance. Theta is independent of everything, but here R is dependent on theta, HKL, and kind of substance. So if we will take two compositions, so for one composition we denote gamma, another composition we denote alpha. We will take a ratio of them. This C gamma by C alpha obtained from measurement of I gamma by I alpha. So here R gamma R alpha can be calculated from crystal structure and lattice parameters. So once this C gamma C alpha are found, then we can write C gamma plus C alpha as so an absolute measurement of certain phase of a material can be obtained using this formula. So if we have more than two phases, then this can be made into, we can add several phases, and from this equation and compare it with this ratio, we can find out this value of C's basically. And next, for internal standard method, here diffraction line from phase determined compared with the line from a standard substance mixed with sample in known proportion. Diffraction line from the phase being determined is compared with a line from a standard substance mixed with the sample in known proportions. So it is restricted for, it's only restricted to powder form. Next, moving on to stress measurement. So when a polycrystalline piece of metal is deformed elastically in such a manner that strain is uniform over relatively large distances, the lattice plane spacing in the constituent grains change from the stress-free value to some new value corresponding to the magnitude of applied stress. This new spacing being essentially constant from one grain to another for any particular set of planes similarly oriented with respect to the stress. So this macro strain causes a shift in the diffraction line to new 2 theta positions. So when metal is deformed plastically, the lattice planes usually become distorted in such a manner the spacing HKL set varies from one grain to another or one part of a grain to another. This non-uniform microstrain causes a broadening of corresponding diffraction lines. So both of kind of strain are usually superimposed in plastically deformed crystalline materials, and diffraction lines are both shifted and broadened because not only do the plane spacings vary from grain to grain, but their mean value differs from that of the undeformed metal. So various methods of stress measurement differ only in the kind of strain gauges used. For example, in the electric resistance method for the measurement of applied stress, the gauge is a short length of fine wire or foil cemented to the surface of metal which is being tested. So any strain in the metal is shared by the gauge, and any extension or contraction of the gauge is accompanied by a change in this resistance, which can therefore be used to measure the strain. So in X-ray method, the strain gauge is the spacing of lattice planes. So in principle, X-ray method is applicable to any crystalline material which, while it has some application to strain measurement in ceramics and rocks, but its major use is the measurement of residual stress in metals and alloys. So how it is done, how the stress is measured in XRD. So here a bar is considered with pure tension with diffraction planes parallel to its axis. It is under a tensile strain. So here stress is given by this y-axis, this is z-axis, and into the surface x-axis. The stress is given by force by area, and this stress is only normal stress acting. There is no shearing present here, and the strain is given by change in length by the original length, final by L final length minus original length by original length, and the stress is related to strain by a constant E, which we have seen in many of, like in Young's modulus, shear modulus. This modulus can be anything depending on the stress and strain were applied. So the elongation of bar is accompanied by decrease in its diameter d. So there is another strain being applied equals to change in its diameter by the original diameter. Let's say the bar is isotropic, so we say strain is related by Ex equals to Ez equals to E times Ey. This mu or mu times Ey, this mu is called Poisson's ratio for the material of the bar, and it ranges from 0.25 to 0.45 for metals and alloys. So to measure Ey here by X-ray would require diffraction from planes perpendicular to the axis of the bar, which is impossible. The diffraction planes parallel to the axis of the bar is used by making the back reflection X-ray measurement. So here it is essential that the back reflection technique is used to get sufficient precision in the measurement of plane spacing, though large stress causes a very small change in the D. So here in Z direction, the strain can be written as dn minus d0 by d0, where dn is the spacing of planes parallel to the bar axis. Parallel to bar axis under stress. And d0 is the space of the same plane in the absence of stress. So we can write stress as minus E by nu dn minus d0 by d0. So here we can note that Only a particular set of grains contribute to a particular H-scale reflection, and those grains which are parallel to the surface of the bar and which are compressed by applied stress can only be seen here. Now moving on to the problems. The first question, the pattern of aluminum made with copper K alpha radiation contains 10 lines whose sine to theta values are 0.118, 0.148, so on. So we have to index this line and calculate the lattice parameter for those. So aluminum has a cubic crystal structure, so we can assume that. And for a cubic structure, T square HKL is given by K square plus L square by A square. From Bragg's law for first order, lambda equals to 2d sine theta, and here from this two equation we can say S by sin square theta equals to 4a square by lambda square. For copper K alpha radiation, lambda given by 0.1542 nanometer. So from here we can say A is given as lambda root S by 2 sine theta. The lambda we know. So let us assume that FCC aluminium is FCC. So for that, if we calculate all the values, we'll make a table like this. And we will calculate the value of lambda. So for all lines 1 1 we will calculate the values. For sine square theta 0.1118, as we are considering FCC, for FCC we can only have all odds or all evens. So here is H scale value can be written as 111, so S will become 3 and S by sine square theta will become 26.833, and from we can calculate A as 0.399. Similarly, for sine square theta 0.1487, H scale value will denote 200, so S becomes 4 and the ratio becomes 26.899 and the A value becomes 0.4. Similarly for 294, the H scale value 220, again here all are even, so it's possible in case of FCC, and S becomes 8 and the ratio becomes 27.2108. They become 0.402. Similarly for 403, we consider 311, the S become 11 and the ratio becomes 27.295, so on. They become 0.403. and accordingly for different sine square theta we can take H scale values and we can calculate the A values, and we can see S by the ratio S by S sine square theta is a constant for all line, and our assumption it as a FCC is correct, and with A we can say it is as 0.4 nanometer. So moving on to next question, an X refractometer recorder chart for an element that is either a BCC or a FCC crystal showed diffraction peaks at 2 theta angles, respective 2 theta angles. The radiation X-ray has wavelength of 0.15405. So we have to calculate the crystal structure of the element, that is parameter, and I have to identify the element. So element is having BCC or FCC, so it is a cubic structure. So for cubic structure, again we have d square HKL, that's a square by h square plus k square plus l square square, and same for A. We can write lambda by root s by 2 sine theta, where lambda is given here 0.5405 kappa k alpha. So we have to do it for both of them, FCC as well as BCC, and we have to check, and we have to see whether it is correct or not. So for FCC, we will consider all even or all odd, but in BCC our h plus k plus l, the sum of h plus k plus l should be even or 0 when h plus k plus l is odd, right? For FCC, and here h plus k plus l even, then we are getting BCC values. So if we consider as FCC, again we make a table, line 2 theta sin square theta HKL S sin square theta and A for 40.663 sin square theta will become 0.120 and HKL all odd. Let's we consider the lowest 111, S value is 3. See, we can here how we are adding the values 2 theta from low to high, and similarly S value from low to high. For line 2 it is 47.314 as per the 161, HKL become 200. For S4 the ratio becomes 4472 and the A value become 0.387. For next theta value, for theta will become 0.322. For HKL 220, the S will become 8 and ratio remains the same. And for the last one, all odd, So here we can see all A's are having almost same value, 0.384 nanometer. So here the assumption for FCC is correct. We can check it for BCC too, and whether A remains same or not we can check. And for FCC with structure with lattice parameter equals to 0.384, we can check the element. For iridium, lattice constant is 0.34. The element is iridium. Next question. Here in the figure we can see 4 peaks at 43.54, 50.83, 74.59 and 90.34. The X-ray diffraction pattern for copper that has FCC crystal structure, and a monochromatic X-ray used to get this pattern has a wavelength of 0.1542. So we have to index each of these peaks and calculate the interplanar spacing and determine the lattice constant. As it is FCC, only planes with unmixed HKL will give diffraction. So D spacing can be calculated from Bragg's law as lambda by 2 sin theta. So let's make one table here. LSD A. Okay. Well, let's say for theta 43.54 and square theta is 0.3709, and for unmixed 111 lists S value of 3. D is found to be 0.2079. From that we can calculate the value of A as 0.3600. How can we calculate this R copper? As it is the FCC, so root 2A equals to so from A we can calculate the radius of copper 2.46. So for 50.83 sin square theta becomes 4292. For S value to be 4, D becomes 0.1796 and A becomes 0.3592 and radius becomes 2543. For third angle 74.59, sin square theta becomes 0.6059, and for HKL 220 having S value 8, D becomes 0.272 and A we can get 0.3598. How we are getting this A? This A equal to lambda root S by 2 sin theta, and R becomes 0.2542, remains the same. For 90.34 sin square theta becomes 0.7092, HKL value 113, S becomes 11, and corresponding to that T value is 0.1087 and A becomes 0.360. We can see the radius is 0.254 nanometer, corresponding to That is constant of 0.36. Moving on to next question. Which among the following function is not used for profile fitting of an XRD pattern? For XRD pattern, we use Gaussian, Lorentzian and void function. The linear function will be the answer for not fitting the XRD pattern. Which among the following factor doesn't contribute to the peak broadening in an XRD pattern? For peak broadening, crystallite size, microstrain, and what type of instrument we are choosing, they all contribute to the broadening of the peak. Only the crystal structure doesn't contribute to the broadening of the peak. What is the condition to be satisfied by the standard sample, which is used to determine the instrument broadening? For instrument broadening, the sample has to be large grained and well annealed. If it is not well annealed, then it will not be proper. We will not be able to identify the sample properly and cannot be distinguished from the instrument broadening. So it has to be large grained and well annealed. Now the sequence 3, 8, 11, 16 represent what class of material? It represent diamond cubic. As we have discussed, for FCC, the values varied from 3, 4, 8, 11, 12, 16, so on. For simple cubic, get a value of 1, 2, 3, 4, 5, 6, 8, so on. And for BCC, we get values like 2, 4, 6, 8, 10, 12, so on. This value we have already calculated in terms of structure factor, where for FCC we have seen for HKL all has to be same, like all has to be odd or even, and from that we get these values. For simple cubic, all the planes are accepted, satisfying S square plus K square for A square condition, and BCC, this S square plus K square for A square should be even. The sum of the squares should be even. Then only we'll get BCC peaks. The intensity of X-rays diffracted by monoatomic gas, this decreases with diffraction angle. So in X-ray diffraction, different peaks which we have seen for crystals, we get for different diffraction angle, we get a particular peaks at particular value of 2 theta and 0 for other. And for liquids or amorphous solids, we used to get a broad peak when we plot diffraction angle with intensity, and this broad peak shows a statistical preference for particular interatomic distance. Preference for particular interatomic distance. And for monoatomic gas, we got a graph like decreasing curve, the intensity versus diffraction angle is plotted, and this shows no statistical periodicity and featureless. So here the answer will be decreases with diffraction angle. Quantitative analysis in XRD is based on peak intensity. As we have already discussed, quantitative analysis by diffraction is based on the fact that intensity of the diffraction pattern of a particular phase in a mixture of phases depend on the concentration of that phase in the mixture. So it is an intensity dependent parameter which is measured. In XRD, direct comparison method is used for quantitative analysis. There are three methods being used in quantitative analysis: external standard method, direct comparison method, and the internal standard method. And quantitative analysis methods are used: external standard method, a line from pure alpha, there is no mixture of phases present here, and then direct comparison method, a line from another phase in mixture, and third one, internal standard method, here a line from a foreign material mixed with specimen, and then we do the measurement mixed with a known specimen basically. Bragg-Brentano diffractometer, the circle on which the source, sample and detector lies, is known as focusing circle. So in Brentano diffractometer, X-rays diverge from the source. The reflected X-rays from sample on the focusing circles are directed to their respective places back on the circle, and we get different reflections from that. So we have a circle like this. Here we have a random powder mount. This is a goniometer. Circle. So here we have a source which will be constituting one circle, and we have detector here. For different sources, different circle are there, and different detector for the same. So this Bragg-Brentano geometry allows for a constant distance between the sample and the detector. It essentially requires that distance from the source to the sample and the sample to the detector, and that the sample is kept on the tangent of the focusing circle. So in order to keep the detector distance constant, the sample must rotate half the angular velocity of the detector. As the angle incidence changes, the detector must move 2 theta, that is 2:1 ratio. So here source, sample and detector all lies on the focusing circle. So the main reason for using a flat specimen to take advantage of focusing action described below, and increase the intensity of weak diffracted beams to a point where they can accurately measure. So basis for this focusing is given by a geometrical theorem, like all angles inscribed in a circle and based on the same arc SF are equal to one another and equal to half the angle subtended at the center by the same arc. Suppose the X-rays proceeding in direction SA and SB encounter a powder specimen located on the arc AB, then the rays diffracted by the same h-scale planes at points A and B will be deviated through the same angle 2 theta, but this deviation angle 2 theta are each equal to 180 minus alpha, which means that diffracted rays must proceed along AF and BF and come to a focus at F. So you can see here focusing geometry for flat specimens. You can see a normal specimen This is focusing circle, and this is normal specimen. This is forward reflection. And for back reflection, this is a focusing circle. This is a diffractometer circle. This applies to a flat specimen used in theta to theta, also termed as Bragg diffractometer diffractors. Bragg diffractors. So for any position of the detector receiving a slit F and the X-ray source S are always located at the diffractometer circle, which means that the face of the specimen, because of its mechanical coupling with detector, is always tangent to a focusing circle centered to the normal to the specimen and passing through F and S. The focusing circle is not of constant size but increases in radius as the angle 2 theta increases. The perfect focusing at F requires that specimen be curved to fit the focusing circle. So the use of a flat specimen causes more broadening of diffracted beam at F and small shift in line position towards smaller angles, particularly at 2 theta angles less than about 60 degree. So both effects can be lessened by decreasing the divergence of incident beam at the expense of decreased intensity. Which of the following is not an application of XRD analysis? So here we do quantitative analysis. We have discussed. We do the phase identification and we did the stress measurement. We didn't do any morphology analysis. So this will be the answer. For residual stress measurement, what is the nature of X-ray beam falling on the sample? That will be parallel, as we have discussed.